IAB members, fellow classmates, as well as professors. My name is Alfonso.
My name is Pedro. Chaviano.
I'm Carvajal.
My name is Jorge, Silva.
And our project is the Robotic Tool Supplier. Now, our robotic tool supplier is going to be a spherical robot meant to assist people on the job. It's not meant to completely erase a toolbox or maybe a tool belt that people are meant to carry out in the working field, but it is meant to assist people carrying heavy items or even in search and rescue situations where you can drive the robot out to a field or where anyone might be currently in an emergency situation and deliver things if they can aid their survival. Now the robot, other than being spherical, will have two arms on its side which will extend and deliver the tool and or utensil which is intended to help the user. Now, the robot's large wheel diameter is going to allow it to not only ride uphill, but also travel over obstacles. Its two drive motors will allow it to both travel forward, backwards, and spin on its own axis when driven in opposite directions. Now, it is a little bit of a con that it is a sphere, the fact that it is a little bit bulky, but by driving both motors in a different direction and spinning on its own axis, it can be driven in very tight areas. Now I'm going to pass it on to Pedro.
So in our research, we came across multiple design options. The first one is an internal RC cart, but this is a disadvantage because it has the potential to reduce friction with the internal surface of the sphere if it runs into any obstacles. The second is the pendulum turning, and this takes advantage of the sphere's center of gravity to rotate left and right as it's moving forward. And the third one is multiple mass shifting, and this is a disadvantage because the complexity of a lot of moving components within the sphere. So we were inspired by two robots. One uses the pendulum, and the second one uses flywheels, and we decided to combine both components. First one is GroundBot, and GroundBot is currently commercially sold for security purposes, and it uses the pendulum motion. And the second one uses the flywheels, and it takes advantage of gyroscopic perception to reduce any unwanted rocking in our sphere. And it was made by Gabriel a student from Carvajal State University. So this is our first prototype. As you can see, for our future stress analysis, most of the load is at the center of the shaft, and one of our challenges will be to find a certain material that has the strength to withstand the torque and the load at the center. And you can see on the sides will be where the tool will be distributed outside. And so for some mechanical components, we're going to be using a motor, flywheels, and also a gimbal. And the motor and flywheel will be at the center cube of the chassis, but the gimbal, which is currently used for GoPros or cameras to be stabilized, so that if our tools will be on the gimbal, and if it would run into any obstacles, it would eliminate any unwanted forces. And we'll also be using gears and bearings, which will allow the shaft to rotate without rotating our chassis. And some specifications, our diameter will be 2 feet, and will weigh around roughly 50 pounds. And our load capacity is about 100 ounces, and which an average hammer weighs around like 20 ounces, so we're roughly seeing about like 5 tools in our robot. And we plan to have a speed of 2 miles an hour, and some 2 to 5 miles an hour, and some examples of the components that we can carry are nuts, bolts, screws, wrenches, hammers, and screwdrivers.
So, like Pedro said, we're going to be using the pendulum turning control for our robot. We're going to utilize the 2 flywheels as gyroscopes, and the flywheels, they're going to store the angular momentum, and that's going to help eliminate any unwanted bobbling in our sphere. The gyroscopes are also going to allow the sphere to spin on its own by manipulating those flywheels. Our sphere is going to be a universal design. This could be tailored for just separate applications, like you can have one for a teacher that's specifically made for that, or for a mechanic in a shop, or an artist, but we're going to have one that's universal that can be used by anyone for any small items that can be placed inside the robot. Now, this robot can be made to be autonomous with computer controls, but since our time schedule is pretty tight, and to eliminate complexities, and this is going to be more of like a proof of concept, is we're going to use RC. It's going to be RC controlled, and in the future this could be easily changed to be computer controlled. Here's a very brief overview of the cost of our main components. As you can see, these are just the main components as we get into the prototyping phase and the manufacturing. This cost is surely to go up as there are some unforeseen components and stuff that we might need to purchase. Here are some of our standards that we're going to be using for our design. We're going to be using the ASME Code of Ethics, their safety standards, metric systems, and their conventions for drawings and tolerancing. Our robot will also be in compliance with the International Federation of Robotics. And for any circuitry and electrical components, we're going to be using the Institute of Electronic and Electrical Engineers standards. And for while we design our gears, we're going to be using the AGMA procedure for gear selection, as well as the ABMA selection for our bearings. And now I'm going to pass it off to Jorge.
Good morning. Our main goal for our tool supplier is to be affordable and reliable. So much so that people all around the world can acquire one. For the global design aspect of our project, we would like to achieve some goals. The first one of them being that the tool supplier should be able to provide assistance to people in any line of work, like mechanics in a shop, doctors on a hospital, or teachers in a classroom. Second, the robot, the tool supplier could be remotely controlled by a person to simplify the load of work of a worker on a hard-to-reach location. Third, we would like our project to be open source. We would like people to be able to download the information that we provide and make a tool supplier. In addition, we think that with the right amount of information, people can use this information and make the tool supplier their own. Fourth, we would like to use diagrams for assistance to simplify the process with visual aid in a step-by-step manner, so they know what each step should look like and what the final product should be. And finally, we think that thanks to the shape of the tool supplier, it will be able to go over obstacles and debris and assist people in complicated situations or emergencies like a natural disaster. Our project has been divided in two parts, like we can visualize on the project timeline. First, on the first few weeks of our project, we started with the project formulation and the literature survey. We started looking for all kinds of information regarding SVU robots so that we could apply it and when looking for a design. When we gathered enough information, we decided on a conceptual design and we started doing the simulation of the parts and assemble them on SolidWorks. For the second part of our project, on the coming months, we'll start doing the simulation of the individual parts of the tool supplier and before manufacturing, so we can have an idea that the parts will not fail us. Once we are done with the manufacturing, we'll optimize the final prototype before validating and testing the final design. Like stated before, for future work, we'll be finalizing our design and start the modeling of individual parts. We will use CAD software to simulate the parts and the actual final design before they start manufacturing parts and acquiring whatever parts we need, and then finalizing the prototype and testing it. Thank you.
I'd like to open up the floor for any questions.
What kind of analysis are you conducting on your system?
We're going to do a stress test on because most of the stresses are going to be on that internal shaft where the motors are. So we're going to be doing to check for the torsion and all that to make sure that our shaft can withstand all the torque, the high torque that the motors are going to apply. And also on the shell, if there's any, we're going to do a drop test to see how much our shell can withstand like a sort of impact.
Are you doing static and vibratories?
Yes.
Stresses?
Any other questions? Yes?
As a tool carrier, you're going to have to keep the tools level at all times.
Right, that's why we're implementing that gimbal device. That's used on GoPros, like you see there. It uses bearings and it stabilizes the piece itself, so if there's any motion, it kind of compensates for that, and then we're going to be implementing that in our tool holder.
The tool holder mounts on top of the ball somehow.
No, it's held within the sphere.
So how do you get the tools out of the sphere?
If you want, like up there, you see where those caps are on the end of the sphere? Those parts are going to always be on the side of the sphere, and that's where our robot arm is going to pop out to dispense the tools.
Sorry, I might have missed. What material are you using for the outer shell?
We're looking at different plastics right now, and we're probably going to use a coating on the plastic to help for traction and gripping. So we're looking at different rubbers for that type of external coating. But the shell is going to be made out of plastic.
And how many flywheels do you use?
Well, we're going to have two.
And how do you handle? So what axes will those flywheels be on?
Pedro?
So the axes will be, they'll be changing from, they'll be on the X and Y, but they'll change on the Z axis to apply an extra torque if they want to go over any obstacles. And they will rotate in opposite directions to reduce any unwanted rocking using the gyroscopic projection.
So by design, it's really only going to be able to turn in this type of a direction. It won't be able to turn in this type of direction.
Well, that's what we're incorporating the pendulum. So the pendulum, while it's moving forward, it will be able to rock the sphere sideways. So it can turn left and right, and it will be able to maneuver backwards as well.
So really, where my question plays is, what is the benefit of a sphere over a series of two wheels
Well,
when you're trying to keep a tool
Right.
Carrier level?
this sphere, we thought that it could go over water if we make it airtight. So that's another benefit of this sphere robot. Is when we were doing research, we saw some of the examples of like that ground bot was able to go over water. So since we're kind of looking at more of, like one of the applications is like disaster relief and to help emergency situations. So being able to be airtight and go over water can really help in that situation.
What kind of waterproofing are you doing on this?
Well, the shell is going to be self-contained, everything inside, and the caps, we want to make it so that it's airtight, and when they release, it'll open out and let the robot arms come out. But when it's closed, it should be airtight.
So all the latching mechanism is inside of the sphere?
Right.
And how big is the sphere?
2 feet in diameter.
What's the maximum load you'll be able to carry?
We had it up there, it was
100 ounces per
100 ounces.
Just 5 tools. This is our prototype.
Yeah, so this could be scaled up or scaled down depending on the application. Any other questions? Okay, thank you very much.